Oh, for today's lesson, we'll be looking at the assignment questions, and that's based on lesson 4.2, combining functions algebraically. So today, I'll take up some of the questions from pages 278 to 281 of your textbook, making a question number 3 to number 11. So I will not go through every single question, but I'll go through select questions and give the complete solutions. The rest of the remaining questions, I will post the complete answers on the blog. Then I'll look at lesson 1, questions 1 to 4 in your combining example booklet, just this one that you have. So we look at lesson 1, and there are 4 questions. So we have looked at example 1, example 2, example 3, and then example 4. And your assignment for today would be example booklet, lesson 2, questions 1 to 4. That's from your booklet, and this is due at next class. So looking at example 1, example 2, and then 2 more examples. So this is due the next class. Okay, before I go into the assignment questions, let's recap what we've done so far in lesson 2. So in lesson 1, we composite graphs. So this is what we did lesson 1. We sketch the graphs of functions that are sum, difference, product, or quotient of 2 functions. Then lesson 2, which we are finishing off today, write the equations of functions that are the sum, difference, product, or quotient of other functions, then determine their domain and ranges. And the previous lesson, we concluded that given 2 functions, f of x and g of x, another function can be defined by adding, subtracting, and multiplying f of x and g of x. And in conclusion, we did a few examples, that 2 functions, f of x and g of x, are, when they are added, subtracted, or multiplied, the domain of a new function is a set of values of x that are common to the domain of f of x and g of x. And then we look at a few examples, and the first example was writing the equation of a function that is a combination of functions. Example 1. Then we looked at example 2, writing the equation of a function that is a quotient of a function. And then we look at the sum or difference of functions. And the final example, writing a function as a product or quotient of functions. So moving on from yesterday's lesson, or the last lesson, on combining function algebraically, we look at these questions from your textbook. As I said earlier, I'll go through a select set of questions, and the rest of the questions that I do not cover in this video, from pages 278 to 281, I'll post them on the blog. So let's look at the first question. It said, given f of x equals x to the power 3 and g of x equals x squared plus 1, write an explicit equation for h of x equal f of x plus g of x. So we're given f of x and we're given g of x. So to write the explicit equation, we substitute f of x into f of x, which is x cubed, and x squared plus 1 for g of x. So we have h of x. I'll use a different pen, a little bit. So h of x, now f of x is x cubed plus x squared plus 1. So that's function. The next we have d of x. Now f of x is x cubed equals x cubed minus, now we have x squared plus 1, and we can expand that. We have x cubed minus x squared minus 1. Now here's a product. So here we have some difference. See, there's a pattern. And here we have p of x. We have x cubed multiplied by x squared plus 1. I can remove this bracket. It looks x cubed into x squared plus 1. Q of x. So f of x is x cubed, and g of x is x squared plus 1. So these are the explicit equations. So question 4, for each function h of x, below here, write explicit equations for f of x and g of x so that h of x is the sum of f of x plus g of x. So what we have here, we have to break it up into f of x plus g of x and still maintain the original function. So we have h of x here. Now, if you were to make this f of x, and this is plus, make this f of x, and this becomes g of x. So we'll have now h of x will be equal to x squared plus, I'll just put this in bracket, 3x minus 4. So because f of x will be equal to x squared, and g of x, we make that as 3x minus 4. Okay, here we have x cubed minus x squared plus 8. So we'll do for the I, this would be I here. So I, so we have h of x is equal to, now I have to add these two. So we'll have, if you make f of x as x cubed, now you can do this in any order, but as long as you maintain the original function. I could make it as f of x as h. This would be a g of x, and this could be f of x. And because it's for subtraction, but for addition, we need to change the sign. So I'm going to make this for f of x plus g of x. So I'll make this as my f of x. So x cubed minus x squared plus 8, and that will satisfy. So I'll make f of x equals x cubed minus x squared, and g of x equals 8. Now let's look at the difference. So we have h of x equals f of x minus g of x. So I will make f of x equals 3, and this will be my g of x, but I'll subtract it, but I need to change the signs here. So if you make this as h of x, so f of x is x cubed minus, that'll be x squared minus 8. So f of x equals x cubed, and g of x, x squared minus 8. Now, we'll go back to this one here. We'll look at your difference, which is h of x is equal to f of x minus g of x. So in this case, I will make this as my f of x, and this would be subtracting. Notice I need to reverse the sign. So this will give me x squared minus, now, minus 3x plus 4. So f of x is equal to x squared, and g of x will be equal to minus 3x plus 4. Okay, let's go on to question 5. Follow a similar pattern as question 4. Now, because it's similar, I'll just do this one question and then we'll skip a few others. So question 4 is similar to question 5. So we follow through this. We have f of x plus, so we have f of x is 2x plus minus 4, and g of x is minus x plus 2. So write this as h of x is equal to 2x plus minus 4 plus minus x plus 2. Simplify, we end up with x minus 2. Here I have h of x is equal to negative x plus 2, because that's my g of x, plus 2x minus 4. So minus x and x will give me x, 2x, minus x and 2x. And you have 2 minus 4 gives me negative 2. And here we have a difference. So we have h of x, f of x is equal to 2x minus 4 minus g of x, which is minus x plus 2. Combining the like terms, end up a result. Well, 2x plus x here give me 3x. And we have minus 4 and minus 2. Gives me minus 6. So here we have hx is equal to, we have gx, which is minus x plus 2 minus f of x. So I'll put that in bracket, 2x minus 4. So expands, we have minus x plus 2 minus 2x plus 4. So we have minus 3x, because we have minus x minus 2x, it means minus 3x. And we have 2 plus 4 equals 6. And here we have h of x. Now we're multiplying these two, so we have what, 2x, well, here, read it down a little bit here, 2x minus 4, multiplied by minus x plus 2. So we have 2x squared plus 8x minus 8. And the last one we have here, we have h of x is equal to, we have minus x plus 2 multiplied by 2x minus 4. So h of x is equal to minus 2x squared plus 8x minus 8. Now, part B asks you, for part A, compare the answers to I and 2, and for parts 3 and 4, and parts 5 and 6, explain the result. Now, if you look at the answers here, no matter what order you put these in, whether you put minus x plus 2 as f of x, or on g of x as 2x minus 4, you'll end up with the same result. Because addition, what we call, is commutative. In other words, it doesn't matter what order in which you do them, you'll have the same result. So if I have minus x plus 2 plus 2x minus 4, I'll still end up with x minus 2. Over here, I have 2x minus 4 plus minus x plus 2, I'll still end up with x minus 2. Same as here, no matter what order. So the order is the same for here. For part 5 and 6, no matter which order I multiply, if I take g of x times f of x, I'll end up with the same result as I multiply f of x times g of x. You have g of x times f of x. Notice I'll end up with the same result. So the same result happening, regardless if I'm multiplying or adding composite functions. So we can conclude that this part here, by the way, is opposite. Sorry, this part is because here is negative 3x plus 6 here, and there's 3x plus minus 6. So this is opposite, so it's different. So let's look at it. So for the answers to part A, to I and to I are the same because addition is, and the word we use here is commutative. The order of addition doesn't matter. Now, notice for 3i and 4, so for 3i and 4, here we are subtracting. So the answers are opposite. Notice the answers here are opposite. Because the order matters. In other words, if I were to take 5, and a good example would be if you take ordinary numbers, say 5 minus 4, the answer is 1. But if I reverse the order, 4 minus 5, the answer is negative 1. So that's why we have, in subtracting, we have opposites. As compared to here, we have like 4 plus 3 equals 7, or 3 plus 4 would be equal to 7. So the word we use here is commutative. And if you look at 4 and 6, this is for 4, sorry, 5 and 6, 5 and 6. The answers are the same. 2x squared plus 8x minus should be minus here. Oh, made a mistake there. It should be the same. Answers are the same. And it goes back to the same similar rule. Because multiplication is commutative. The order doesn't matter. So the order of addition, the order of multiplication doesn't matter. So for example, if I have 4 times 3 is equal to 12, or 3 times 4 is also 12. So it doesn't matter if the 4 you look at 4 groups of 3 or 3 groups of 4, you still end up with the same result. Okay, I'll do a couple more examples. Let's look at example 6 or question 6. And they ask you to state a domain after writing the composite function. So we have k of x, and we're given f of x and the g of x and h of x. So we'll substitute the given function into our composite function here. So we have k of x will be equal to f of x is x squared minus 4 plus we have g of x is 2x minus 1 plus h of x is 3 minus x cubed. Combining like terms, so we have x squared minus x squared will give this x cubed. Oh, sorry, we have x squared. That's the only one x squared we have, but we have a negative x cubed. So with the negative x cubed, then we have plus x squared. Now when the x's, we only have 2x. And then we have negative 4, negative 1, and plus 3. So we have negative 5 plus 3 will give us negative 2. Now this is a cubic function, as you can see. Y negative. And we know from our previous lesson that a negative x cubed is a graph. All of the domain is the domain is from negative infinity to infinity. So the domain would be x elementary real numbers. The line across, so separate. Now this following question, now it's k, we're subtracting g of x. So we have x squared minus 4 minus g of x. Now I'll just put a bracket around, so it helps me in my combining like terms, plus h of x, which is 3 minus x cubed. Combining like terms, we have x squared, we want x squared, we have an x cubed, and that's negative x cubed. And we have 1x squared positive, oops. And then we have negative, 2x, we have negative 2x here. Negative 4, and here we have plus 1, plus 3, so we end up with 0 there. So that's my final answer. There's another cubic function, so cubic function. So domain, elementary real numbers. So the next one we have k of x. Is equal to, we'll substitute our value. We have x squared minus 4 plus 2x minus 1. I'll put in bracket because we multiply here. Multiply by 3 minus x cubed. So k of x, we have x squared minus 4 plus, multiply these out. We ended up with what, 6x, 6x, then we have, how many x cubed we have here? 2x times 3, and we have 2x times x cubed will give me 2x to the power 4 negative. And we have negative 1 times 3 give me negative 3, and negative 1 times negative x cubed give me positive x cubed. So combine them, so there's 1x cubed to the power 4. So negative 2x to the power 4. 1x cubed, so we put that in. Then in the x squared, we just have 1x squared plus. We have x's, we have negative 6, or positive 6x. Then we have negative 4, negative 3, positive 7. This is a function that's a quartic. Power 4. So the domain x equals. Here we have a product and a difference. So k of x put these in bracket, 2x minus 1 multiplied by x squared minus 4 subtract 3 minus x cubed. Well, probably can't notice. Let's put it down so I can continue to see what's up there. So now k of x, combining them, so we have 2x times x give me 2x to the power 3. Then we have minus 8x minus x squared plus 4 minus 1. Then we have minus 3 plus x cubed. Combining everything, we have 3x cubed. So you have 2x plus 1 cubed minus x squared minus 8x plus 1. So it's a cubic function. So we say the domain x elementary numbers. Okay, we'll look at question 7. And here we give the function x squared minus 3x minus 28. Write explicit equation for 3 function, f of x, g of x, h of x, so that k of x is equal to f of x plus g of x plus h of x. So we'll change this function in its form, but maintaining the function as it is. So we can make this f of x. We can make that g of x and h of x. Make those 3 separate functions. So it's really a composite of sums. So we have f of x, k of x. So here, if we make f of x as x squared, which I'll write right under here. Now, we need to add plus, we put in bracket, negative 3x. And here we need to add, now this would be negative 28. So here we have our f of x is equal to x squared over g of x is equal to negative 3x, and our h of x equals negative 28. final, so our sample response is that we take the function given here, which is a quadratic, and factor it. By factoring it, we have two binomials and multiply the binomials. We'll still maintain that function. So we have k of x will be, here we have negative x squared minus 3x minus 28. So we'll factor x squared minus 3x minus 28. So this will give us our f of x and g of x. So we have x and x. Now, if we look at this, we have, what are the factors of 28? It'll work, so it'll give us 7 and 4. So we have plus 4 minus 7. So k of x will be equal to x plus 4, x minus 7. By the way, you could have put this in a different order. You can make f of x, x minus 7, and g of x, x plus 4, and it will be the same. So f of x, this, and g of x in this case. Or you can do it the other way around. You could have said this is f of x, so it'd be x minus 7 should be f of x times x plus 4. As we learn in question 6, question 6, we learn in question 5, when we are multiplying, the answer is the same because multiplication is commutative. The order doesn't matter. So that's why we can switch these and still maintain the function. Okay, I will do one last question from this part here. Question 8. So I'll do one section here and I'll post the other answers on the blog. So for each function h of x, we will write an explicit equation for f of x and g of x so that the sum, difference, and the product along the quotient. So we have 4 of these. So we have x squared, and we have to change x squared into 2 functions, but still maintain those composite functions as x squared. And the easiest way to do this is that we can make f of x as x squared, and then we subtract it as g of x. Or we're going to add it of g of x and multiplying it. So let's see how this will look. So we can subtract and add the same term. And it doesn't matter what term you use, it will be the same as long as I subtract and add. That's for the first one. So let's look at, so we have h of x must be equal to f of x plus g of x. So we have f x squared. So So if we add and subtract, in this case, we have x squared plus, we're going to subtract it, right? So we have h of x squared. So g of x now, we need to add and subtract. So we're going to add it. If you're going to plus the add, it will be x minus x. This becomes 0. So for addition, right, so we add and subtract. So we should be adding first and subtract, and change this over here. We add and subtract. Because we want f of x plus g of x. So f of x is going to be equal to x squared, and g of x is equal to x minus x. Now, we'll subtract and add for the subtraction for the difference. So we have h of x is equal to f of x minus g of x. So we have here, in this case, so we can make this f of x as x squared minus x squared plus x minus x. So f of x is equal to x squared plus x, and g of x is equal to x. So that will give me my same result. X squared plus x minus x will still give me x squared. So this is the sum difference. Now we do product. So h of x is equal to f of x times g of x. So all what we'll, so write back my h, give me my h of x is equal to x squared. So by factoring this, we give x times x. So h of x is equal to x times x. So f of x is equal to x, and g of x plus x. And the final we have is a quotient. So we multiply and divide x squared by the same non-zero expression. And there are many, many you could use here. So here we're going to multiply and divide x squared by same non-zero. Be careful about this. Non-zero expression. So, for example, we have h of x, give x squared. So it doesn't matter what, as long we have a non-zero, such things, non-zero would be like x squared plus 1 or x squared plus 2, etc. So we can have x, each of x is equal to x squared to x squared plus 2 over x squared plus 2. This is non-zero. So we have f of x is equal to x squared into x squared plus 2, and g of x is equal to x squared plus 2. So I'll post the other, I'll post the other questions, the answers, the full solutions for the other questions on the blog. So this is question 8. Okay, that's it for your questions in your textbook. I just would like to go on to the example booklet and look at some of the questions in lesson 1. So this is your example booklet here, chapter 4, combining functions example booklet. So I'll go on to lesson 1. And in lesson 1, you're asked to, you're given two functions, and you're asked to find the composite function, the sum of the functions. So we can do it the shortcut ways and the mapping ways. So I'll show you the shortcut way. So since we're adding f of x plus g of x, so we have f of x here, and you have g of x. So we pick reference point here. We have, look at the vertical line at x equals 0. G of x, f of x is 2, and g of x is 6. So we add the 2 plus 6, because that's what we're doing here. F of x plus g of x. F of x is 2, g of x is 6, for the same 0. So 2 plus 6 is 8. Then you go to the next reference point. We have f of x is 3, and g of x is 4. So 3 plus 4 is 7. Here we have f of x is 4, and we have g of x is 2, give us 4 plus 2, give us 6. And the last one we'll do, we have f of x is 5, g of x is 0, and that's 5. So those are my points by inspection. So now if you were to do a chart, we can do it x f of x, g of x, and our coordinate to be x f of x plus g of x. This is my y coordinates. So we'll end up with the same result. You have 0, 2, 6. So it'll be 0, 8. 2 plus 6. Next point we have is 3. So we have f of x is 3 plus 4. So we have 3. So that's my x value. 3 plus 4, 7. Next point we'll use is 6. So we have 4 plus 2. We give us 6. 6. And the last one we have is 9. Get an extra piece here. Do I need all of space? So remove it. So you have 9. So f of x is equal to 5. G of x is 0, so it's 9, 5. So we end up with the same result. And now we will connect those points. And I'll use a ruler. Equals f of x plus g of x. So this we call a sum. On to the next question 2, example 2. We'll do this now. Here we're subtracting h. We're subtracting g of x from h. So it'll be 20 minus 10 will give us 10. And here we have 25 minus 15 will give us 10. So my next point here. Then I have 40 minus 20 will give us 20. And 80, we got what? 100 minus 30 is 70. So if I connect with a smooth line, so this is my function. Y is equal to h of x minus g of x. Also, you could have done a chart and get the same result. Case of what I have h of x, and this is g of x. So the h of x minus g of x. So we have 0. H of x is 20. It's 10, so it's 0, 10. Next one is 20. You have 25 and 15, up here. So it'll be 20 and 10. It's almost like a flat line here. And the other two, 40, you have 40 and 20. 40 and 20. And you have 80, 100. 30, so my point is 80 and 70. Okay, let's look at the other two examples. So here we're looking at the product. And so we're multiplying the two. So I'm going to do a chart because I find this might be a little bit much easier. And then we need to find the domain and range of the composite function. So x, f of x, and we have g of x. So my coordinate would be x, f of x times g of x. So at 4.0, let's use the reference point 0. So f of x at 0 is 2. G of x, oh, sorry, f of x 0 is 0. That'll be 0. And f of g of x is 2. So at 0.2 times 0, so it'd be 0. 0 times 2 gives me 0. So my first point is right there. Then the next reference point I go on to is 1. So at 1, f of x is 1. So we put at 1, f of x is 1. G of x, but g of x is approximately 0.6. So this is 1. 1 times 0.6 is 0.6. So it would be roughly about right here. This would be my invariant point, so we can connect those points. And we have 2 more, so we have x is 2. Now, f of x when x is 2 is 4. And g of x is 0. So it'd be 2, 4 times 0, 0. And the last one we look at is 3. So we have 2, 0, just right here. Continue my curve. And for 3, we have what? F of x as what? 3 all the way up to 9. And g of x is roughly around 0.5, negative 0.5. So we have 3, so we have 9 times negative 0.5, which would give us negative 4.5. So at x for negative 4.5 is about here. So this is y is equal to f of x plus g of x. Now the domain, if notice here, is the composite function. So the domain, write that here. So for f of x, you notice f of x is all the real numbers. And for g of x, it's restrictive. The g of x starts from 0. So where x is greater than or equal to 0. And for a composite function, y equal to f of x and g of x. So y equals f of x, g of x. Notice x is greater than or equal to 0. Okay, we have a final question, which is example 6. And here is a quotient. He has to find the domain of h of x divided by g of x. So we'll create a table of values using a chart here. C of x, h of x, g of x. On my coordinate, my points would be x, h of x divided by g of x. So let's start with -4. So -4 for, so -4 first. For h of x is 4. And for g of x, I think it's what we have 2, 6, it'd be a 7. So -7. So it's -4, -4, 7. It's 4 divided by -7. So next point is -3. We have it's 3 and be 0. So interesting, we have -3. Then we have 3 divided by 0. This would be undefined. Since this is since undefined now, we'll have an asymptote right here where x equals -1. So I'll indicate my asymptote. Then we go to -2. -2, we have 2 and 5. So -2, 2 divided by 5. So let's start plot some points here. So for the first one is 4, it's about here. So what we'll notice that this graph would be down this way. Now, it's undefined, so next point is -2 2/5, which is about here. When we go to 1, or -1, sorry. -1 we'll have is 1. And so -1 be 1 and then 8. So 1 and 8. So this gives us 1, 8. So -1 and 1, 8. Should be about here. 0. We have 0 here. And we have x, g of x is 9. So we 0, 0. 6 points right there. And you'll see a similar pattern now. We have 1. Now it's a duplication of a negative. So it'd be 1. And this is 8. So we have 1 and 1/8. Same as this one here. So we have 2, 2 and 5. Same as what we have here, except it's not positive. Three. So at 3 we have, that's where the h of x is 3, and there's 0 here. So this gives me an undefined function because 3 divided by 0, so it's undefined. So this we can asymptote. So we connect these points knowing fully well they're going to go this way. Here we have, now it will be x is 4, h of x is 4. And g of x would be -7. So we have 4. So that's approximately here. Graph will be okay. So to recap, we looked at 4 examples. First one is the functions that are sum. Then we looked at functions, composite functions that are difference. We used a table of values. Then we looked at product and finding a domain. And finally, we have the quotient. Now, I forgot to ask you about the domain. So the domain for h of x is an absolute value function. Domain. So h of x, you can tell right away will be all the real numbers. The domain for h g of x will also be all the reals because it's going -infinity to +infinity. But the domain for the composite function y equals h of x over g of x, well, there are two asymptotes. So we can say x is not equal to -3 and x is not equal to +3.